Now this is known as the photoelectric effect. Photoelectric sounds very complicated, but it's actually a very simple idea. Photons come in and electrons come out. So if the work function energy is the energy needed to just jump an electron out, just dribble it out of the top, what happens if you send in photons with higher and higher and higher energies? So what happens if you get a higher energy electron? That's the wrong way around. Oh no, maybe not. Let's say you want a higher energy electron coming out. How do you achieve that? Well, you fire in a higher energy photon getting in the first place. So if that photon coming in has far more energy than the minimum energy needed, well, where does that energy go? Well, it gets given to the electron as extra kinetic energy. So the work function energy is when the photon comes in and it just dribbles the electron out the top of the block of flats. If you fire in that photon, give it loads more energy, then that jumped out electron doesn't just about get to the top of the block of flats and fall over. It fires out really, really fast. Okay. So if you want to find the kinetic energy of the jumped out electron, you've got to work out the energy of the incoming photon, the incoming photon's energy, which is hf. Hf is always the way we work out the energy of a photon. So this is the energy of the actual incoming photon minus hf subscript 0. Now hf subscript 0, hf is always the energy of a photon, so this is the work function energy, and f0 is the threshold frequency. So the kinetic energy left over, the kinetic energy given to the electron once it's got out of the block of flats, it's, if you like, the leftover energy. If you've got an incoming photon which has a lot more energy than the minimum needed, then that excess, that leftover energy gets given to the jumped out electron. It's sometimes called a photoelectron. And it's one photon in jumps one electron out. One photon in, one electron out, so long as and only if the incoming photon has a high enough frequency or a high enough energy. So it's as long as the photon has a high enough threshold frequency or a high enough work function energy. One in, one out. It's a bit like nightclubs when they sometimes do a one in, one out door policy. So next time you are living at large in DeVito's and they are doing a one in, one out door policy, you can tell them about quantum physics. And that person you're trying to impress will go, "Oh, you're so amazing and intelligent and pretty." And there you go. I bet you didn't think you'd be getting dating tips on physics videos, but you do. Anyway, photoelectric effect. This is proof of the particle nature of light. If you think about the interference pattern stuff we did with diffraction, that's proof of the wave nature of light, but the photoelectric effect is proof of the particle nature of light. So this is the whole wave-particle duality thing. Sometimes light acts like a wave, sometimes it acts like a particle. And again, a bit like the whole Copenhagen interpretation of quantum mechanics, some people get really, or they sort of used to get really hung up about, well, how can a wave be a particle? How can a particle be a wave? Most physicists have now just kind of like, get over yourself. It just, it's a bit weird, but sometimes it acts like a wave and sometimes it acts like a particle. It's just how reality seems to be. Just get over it. Anyway, why is this proof of the particle nature of light? Well, if light was a wave carrying energy, because waves do carry energy, then even low energy red light would gradually float electrons out of an atom if a metal was left for a while. Let's expand on that. So imagine you've gone to Lunan Bay and you've built some sand castles, and the waves from the sea come up and eventually they lap against your sand castle and they carry a little bit of the sand away, and then the wave comes up again and it carries a little bit of the sand away, and the wave comes up again and it carries a little bit of the sand in your sand castle away. And after a while, even very weak waves will kind of float your sand back out down the beach to the sea, and your sandcastle will be away. And so if the light coming in was a bit like water waves, and you had an electron at the bottom, then it would come in and it would push the electron up a little bit, and then the next wave would come in and it would push the electron up a little bit, and the next wave would come in and it would push the electron up a little bit further, and the next wave would come in and it would push the electron up a little bit further, and then each time the electron would be advancing up the block of flats. And even if it was very kind of low energy, weak light, then it would be kind of like a low energy, weak water wave, gradually washing away the sand. This weak, low energy light would gradually shift up and up and up. Even if it's only a little bit, then after a while these electrons would come out, just kind of dribbling over the top. But that doesn't happen. You can leave a lump of metal underneath a low energy, so like a red light or whatever, for as long as you want, and nothing ever happens. But no matter how long you leave it under a red light, electrons never emerge. But as soon as you hit a particular frequency, they suddenly do. So you can leave a lump of metal, and it's different. This exact point, this exact frequency is different for different metals, but you can leave this lump of metal under let's say a red lamp for days and days and days, and no electrons will come out. You can then gradually increase the frequency of the light, and then suddenly loads of electrons start coming out. And if you're thinking of light being a wave, that doesn't make sense. But if you've got the whole one photon in, one electron out, so long as the photon has that sufficient frequency, the threshold frequency, then all of a sudden that behavior makes sense. And actually, furthermore, you can make the light dimmer and dimmer and dimmer until you've essentially got what would be a photon at a time coming in, and then you have an electron at a time coming out. So the current of electrons coming out seems to match up the number of photons coming in, because actually you can turn down the brightness of a beam of light, and that reduces the photons. So if you have a very small number, what would be a very small number of photons coming in, then you end up with a very small number of electrons coming out. If you make it very bright, you have loads of photons coming in, then the current of electrons coming out matches that exactly. So this whole one photon in, one electron out, this particulate nature of light being photons seems to match what's going on. If the SQA asks you to describe it, it's this one photon in, one electron out behavior. And this is how space telescopes work. We know that astronomy is done in many different types of lights, well, the entire lights of the spectrum. And to tell the type of light from a star, so is a star giving out ultraviolet light, or is it giving out X-rays, whatever, then we say, well, as the frequency of the incoming light photons is going to go up, because you're going, for example, from visible to ultraviolet to X-ray to gamma light, so the frequency is going up, the kinetic energy of the jumped out electrons will go up. Do you remember? Any leftover energy goes to the kinetic energy of the electrons. So this is how the different types of light in the universe are detected, because if you have the going up the way, this shows the kinetic energy of the electrons out from the metal. Going along the way is the frequency of the light coming in. So we know there's going to be a minimum frequency needed. This is the threshold frequency, so photons here have enough frequency to eject, but so long as those incoming photons have enough energy to eject in the first place, as the light gets of a higher and higher and higher frequency, so ultraviolet, X-ray and gamma, there's more and more and more energy left over for the jumped out electrons, and so the kinetic energy gets up and up and up and up and up. And this is how digital devices can detect what type of light the star is giving out. The brightness of the image from your space telescope, it's all about the number of electrons coming in. So, sorry, it's all about the number of electrons coming out, because it's the electrons which form the image. And to have a brighter image, you need more electrons coming out. So if you want more electrons coming out to get a brighter image, then you want more photons coming in. Obviously assuming these photons have enough energy to do the electron jumping thing. But If you want a brighter image, then you need more photons coming in. And if you want more photons coming in, then you need a bigger telescope. So this is the argument which space agencies use to get more money from the government. If you want to see further away stuff, then that means you need to have brighter images, because further away stuff is very faint. If you want brighter images, you need more electrons. If you want more electrons jumped out, then you need more photons coming in. And the frequency of these photons coming in is irrelevant, because it's one in, one out. Think of the door policy of clubs. If you want a bright image, it's not about the energy of the jumped out electrons, it's just about the number of the jumped out electrons. So it's not about the frequency of the incoming photons, it's about the number. So if you've got a graph of the brightness, so this is like the number of electrons jumped out, not the kinetic energy, we don't care about the kinetic energy, it's just brightness which decides the brightness of the image. If it's just brightness, it's just the number of electrons involved, and then this is the frequency of the photons. Well, yes, photons have got to have a minimum frequency, but if you're just making those photons have more and more and more energy, but it's the same number, more and more and more energy, but it's still the same number, then you're just going to have the same number of electrons jumped out. Now, okay, those electrons jumped out are going to have more energy, but this upward scale isn't about the energy, this is just the number. So this is, if you've only got, 5 photons coming in, then you're only ever going to have 5 electrons jumped out. And somebody says, oh well, let's make these 5 photons higher and higher and higher frequency, let's make them into UV, X-ray and gamma. What is that? If we've got 5 coming in but they're getting more and more energetic, does that change the number of electrons jumped out? Well, no, it doesn't change the number of electrons jumped out. So yes, this is the I want a bigger telescope graph. It's the only way to raise this, because the way of understanding this graph is understanding that this axis is number. And the only way to raise the number of electrons being jumped out is to raise the number of photons coming in. This axis is irrelevant. This is the axis which matters. It's about the number of electrons jumped out. This axis is irrelevant. Anyway, we've reached a lovely blank wall, which means this section of videos is over. Thank you for listening. Well done. Hope they've been of some use. Another video soon to come, I'm sure. Right, toodle pips.